Hello, hello, testing, testing. Hmm. Hello, hello. Hello, 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 hello. Okay, I think it's okay. It'll do. Um, yeah, just gonna carry on from where I left off yesterday. So I'm gonna start off with my usual Duolingo for Greek, and then I will get on to other stuff. Match the pairs. Snow, snow, sail, seal, seal, stare, stare, sin, sin, osos, seal, stare, stare, snow, snow, os, os, co, co, sin, sin. Select the correct characters for co, co. What do you hear? Co. The cinema, cinema, cinema and museum. Cinema, cinema. Okay. Museo, museo. Stare. Sin, 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 sin. Stare. Oh, stare. To snack. To cinema. Cinema. The snack at the cinema. To snack at the cinema. Yeah. Sin. Type in Greek, keyboard. Greek. To cinema. To cinema. Was that the Z? Oh, it is. It's an S. Okay, fair enough. Cinema. So store. 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 Museo. Mu. Okay. Mu. Mu. Museo. Seo. It's got an I in it. Wow. Okay. Do. Cinema. Sto. Museo. At the museum. Sto. Museo. Great. Cool. Okay, that's that done. So I have to remind myself of what I did now. Gosh, right, yes. So I was trying to figure out what the positions of electrons are in the energy fields on an atom. Right, and we were doing some GCSE bite-sized stuff, or I don't think it was GCSE, it was something else. But I think this was the calculation I had, which was atomic mass times times the abundance plus all of the other ones in that atom divided by the abundance plus together. We had an issue with molybdenum. How do you say that? How do you say molybdenum? Oh, Greek. Whoops. How do you say molybdenum?
Molybdenum.
Molybdenum. Cool. I didn't know that. So yeah, we had this issue whereby molybdenum wasn't coming back correct, and if I go and look at the code that I was running, I think it was in Visual Studio Code. Yeah, this was it. So if I run that. Okay. Yeah, that was wrong because it should have been 95.25 or something like that. So let's go back to our little molybdenum. Yeah, 95.95. Right. Now I couldn't figure out at the time, but it's not what I need to know right now. So I need to know the positions of electrons. Right. So here's the thing. If I go look at hydrogen again, which is this kind of super simple one, it has this electron configuration of 1s1, and I need to figure out what that means. So let's just close these other things for now. Let's find out what this means. Hydrogen has one electron in a 1s orbital, and we write its electron configuration as 1s1. Helium has both of its electrons in the 1s orbital, 1s2. One electron has both of its electrons in. Okay, so wait. Hydrogen has one electron in a 1s orbital, one electron in a 1s orbital, and we write its electron configuration as 1s1. Helium has both of its electrons in the 1s orbital, so it has two electrons. So it's going to be. I wonder what it's. Oh, it's in the 1s, and there's two electrons. I see. Okay. Let's see what this says. Can you see this? Let me just double check. Oh yeah, I forgot to note I've got a new camera, so hopefully it's a little bit cleaner. I can actually see me rather than just noise. Yeah, it looks so much smoother, doesn't it? Cool. Okay. This looks interesting. The answer to our dilemma is provided by quantum numbers whose derivation we will not consider. Basically, we can describe the wave function for each individual electron in an atom by a distinct set of three quantum numbers known as n, I, and ml. The principal quantum number n is a non-zero positive integer, okay, etc. These are often referred to as shells. The higher the value of n, the higher the overall energy level of the electron shell. For each value of n, there are only certain allowable values of L, and for each value of L, only certain values of ml are allowed. The allowable values of L and ml for each value of n, these, are shown in table 2.1. While this may seem confusing, it is the result of these calculations that we are really interested in. That is, the types, orbitals, electron density distributions designated by the set of quantum numbers. There are a few generalizations we can make. Each orbital in an atom is described by the three quantum numbers n, l, and ml, and each orbital can contain a maximum of 2 electrons. As they are typically drawn, each orbital defines the space in which the probability of finding an electron is 90%. Since each electron is described by a unique set of quantum numbers, the 2 electrons within a particular orbital must be different in some way. Let me read that one again. As they are typically drawn, each orbital defines the space in which the probability of finding an electron is 90%. That makes sense. Since each electron is described by a unique set of quantum numbers, the 2 electrons within a particular orbital must be different in some way because they are unique. Describes unique set of quantum numbers, okay? That's very interesting actually. But because they are in the same orbital, they must have the same energy and the same probability distribution. So what property is different? This property is called spin. Okay, I've heard that one before. The spin quantum number, ms, can have values of either plus a half or minus a half. Spin is responsible for a number of properties of matter, including magnetism. Oh, this is really exciting. This is really exciting. Okay, so we've got n, 1, L, 0 to n minus 1 values. ML is minus 1 to 1 values. Is this minus L or 1? Hard to tell. And the orbital name, 1s atomic orbital, and 2s, 2p, 3 different orbitals with different orientations in space but the same energy. 3 different orbitals with different orientations in space but the same energy. Okay. So I wonder what P stands for. Maybe it's poly, many, S single or stable or something like that. 3s spherical but with 2 nodes. 2 nodes. 3p is 3 different orbitals with different orientations in space but the same energy. Same as 2p but with 2 nodes. 3d, 5 different orbitals with orientations and shapes but same energy. 2, 1, 0, 1, 2. This was minus L to L values, or this M minus 1. What is this number? I want to know what you are. I can't copy you. Paste. 1, L. Can I copy any of these? No. Put it up here. That's weird. That is so weird. So some... Wait, can I copy anything? And, maybe? What? Why can I not copy stuff in here? Is that a bug in Firefox? That's a bug in Firefox. Take care when pasting things you don't understand. This could allow attackers to steal identity or please type allow pasting. Oh, okay. Not a bug. Well, that's got to actually read stuff. Ooh. Yeah, okay, cool. Right. No bugs, just annoying. Right. So that is an L, I see. Oh no, is that an L or is that a 1? Yeah, it is an L. Okay, fucking hell. They look exactly the same. No, they don't. Alright, cool. So this is actually minus L to L values. Okay. Right, cool. So, excuse me. Hydrogen has one electron in a 1s orbital, and we write its electron configuration as 1s1. Helium has both of its electrons in the 1s orbital, 1s2. In lithium, the electron configuration is 1s2, 2s1. So this is first orbital, second orbital, which tells us that the electron is being removed from a 2s orbital. Which tells us that the electron is being removed from a 2s orbital. Quantum mechanical calculations tell us that in 2s orbital, there is a higher probability of finding electrons further out from the nucleus than the 1s orbital. Quantum mechanical calculations tell us that in 2s orbital, there is a higher probability of finding electrons further out from the nucleus than the 1s orbital. So we might well predict that it takes less energy to remove an electron from a 2s orbital found in lithium than from a 1s orbital found in hydrogen. Okay, let's just visualize that a bit. So it's saying that if you have this minus, then it takes more energy than one in the second s orbital. So this takes less energy, and this is 2s and 1s, 1, 1. Okay, well that makes sense. I think that's what I'm reading here. Moreover, the 1s electrons, which are a filled shell, act as a sort of shield between the nucleus and the 2s electrons. Moreover, the 1s electrons, which are a filled shell, act as a sort of shield between the nucleus and the 2s electrons. Between the okay, so this is point this is point 1. So let's go down here. Try and understand that. It says if I've got this is the 2s here. Looks like a nipple. Moreover, the 1s electrons, which are a filled shell. So I'm guessing if there are 2 electrons in that first one, which maxes out that shell, one s electrons, which are filled shell, act as a sort of shield between the nucleus and the 2s electrons. Oh, I see. Okay, yes. So if there was, yeah, okay, that makes sense. So it's just simply saying that, let me get a kind of shield like this. So this is, let's label these 2s and then 1s, 2, 2s1, and this is this shield. Okay. In essence, the 2s electrons feel what is called the effective nuclear charge, which is smaller than the real charge because of the shielding of the 1s electrons. Okay, that makes some sense. So let's copy this diagram again. So we've got this. It's saying that, I need to reread it again, I think. The two s electrons feel what is called the effective nuclear charge, which is smaller than the real charge because of the shielding of the 1s electrons. In essence, two of the three protons in the lithium nucleus are counterbalanced by the two 1s electrons. The effective nuclear charge in lithium is +1. The theoretical calculations are borne out by the experimental evidence, a good test of a theory. I don't quite gather this. So the two s electrons feel what is called the effective nuclear charge. Okay, they can feel charge, which is smaller than the real charge because of the shielding of the 1s electron. So the positive charge in the center, let's put this as positive, well, let's make that middle a bit bigger. Let's make it a bit bigger, like that. So this is going to be a positive, and a positive. And this feels less charge because of the shielding happening in this area. Because these are pulling, or these, because these are negating some of the energy in here. Negates some of charge from nucleus protons. Right, I think that's what that means. At this point, you might start getting cocky. You may even be ready to predict that ionization energies across the periodic table from lithium to neon will increase with a concomitant decrease. Oh my god. What does that mean? Naturally accompanying or associated. A phenomenon that naturally accompanies or follows something. With a following decrease in atomic radius. Concomitant. Concomitant. How do you say that?
Concomitant.
Ooh, concomitant. That was nice. Right, in the case of atomic radius, this is exactly what we see. Right, so it says, you may be ready to predict that ionization energies across the periodic table from Li to neon will increase with a continuing decrease in atomic radius. So it's saying as the radius, let's do this, it's hinting, or it's teasing the things that we might be thinking, that if the radius, let's do the radius like so, r, if r tends, or if r gets smaller, E E it says You may be ready to predict that ionization energies across the periodic table from Li to neon will increase with a concomitant decrease in atomic radius. So the energy, if R gets smaller, E gets bigger. Therefore, R, no, if R gets smaller, E gets bigger. That's fine. That's fine. We know what that means. And it says, in the case of atomic radius, this is exactly what we see. See figure. Yes. Good figure. Again, the reason for both these trends is that each electron is attracted by an increasing number of protons as you go from Li to Ne. That is, the effective nuclear charge is increasing. Electrons that are in the same quantum shell do not interact much. Oh, now that's fascinating. Now that's saying that, that is saying they don't interact much. So if I got a negative here, an electron here, then this and this weaker attraction in electrons on the same shell. Do not interact much. Do not interact much. Let me just weaker attraction, weaker interaction, not attraction. Let me just get that word right. Interaction. Okay. Electrons that are in the same quantum shell do not interact much, and each electron is attracted by all the unshielded charge on the nucleus. By the time we get to fluorine, F, which has an effective nuclear charge of 9 minus 2 equals positive 7, and neon, 10 minus 2 equals plus 8, each of the electrons are very strongly attracted to the nucleus and very difficult to dislodge. Okay, so let me just see what's going on here. Fluorine, yeah. So we go back out here. We'll get fluorine, and it's saying the numbers 9, 2, and 7. So the 9 comes from the atomic number, the 2 comes from the not sure where they come from. Effective nuclear charge of 9 minus 2. How to calculate effective charge of an atom. The effective nuclear charge is the net positive charge experienced by valence electrons. It can be approximated by the equation Ah, this is a problem. This word. This is a problem. By the equation Z effective nuclear charge is equal to the Z minus S, where Z is the atomic number, and S is the number of shielding electrons. Okay, shielding electrons. Oh, that makes sense. That makes sense. So if we go and try and figure this out again, so neon is 10 minus 2. Neon, that was N, right? N. Neon is N. Ooh, I don't know. Neon. Can I search? No. Guess it's Ne. Any Ne's? Element symbol for neon. It is Ne. Where is Ne? Anywhere? Is Ne anywhere? Neon, right. So if I click on that, I can see that this should be 10 minus 2 is equal to positive 8. So this will be n minus 2 is equal to positive 8. Great. As you have undoubtedly noted from considering the graph, the increase in ionization from lithium to neon is not uniform. Where's the graph? Here, graphy. No graph. Great. There is a drop in ionization energy from beryllium to boron and from nitrogen to oxygen. This arises from the fact that as the number of electrons in an atom increases, the situation becomes increasingly complicated. Electrons in the various orbitals influence one another, and some of these effects are quite complex and chemically significant. We will return to this in a little more detail in Chapter 3 and at various points through the rest of this book. Yeah, this is interesting. I wonder if this is why things like AlphaFold are just so complex. Because you don't know the definitive positions, you guess through probability of the wave, I suppose the wave functions, and then use AI to predict based on probability too. It's interesting. I don't know if that's true, but just a thought. So, before I continue, what the hell is this? This is great. This is really, really great. virtuallaboratory.colorado.education. Oh, if it's Colorado, we're good. If we use the ideas of orbital organization of electrons, we can make some sense of patterns observed in ionization energy. Let us go back to the electron configuration. Beryllium, Be, is 1s, 2, so it's got 2 electrons in the first shell, and on the second shell there are 2 electrons, while boron is this. When electrons are removed from beryllium and boron, they are removed from the same quantum shell, n equals 2. But in the case of beryllium, 1 is removed from the 2s orbital. You know what? I just remembered I was supposed to read my meters for my apartment. I should go and do that before it's too late. It's too late. Okay, sorry. When electrons are removed from beryllium and boron, they are removed from the same quantum shell, but in the case of beryllium, 1 is removed from the 2s orbital, while in B, the electron is removed from a 2p orbital. While s orbitals are spherically symmetric, p orbitals have dumbbell shaped and a distinct orientation. Dumbbell. Dumbbell. What's that? Oh. Oh, is that a dumb? Okay, I didn't know that. Dumbbell shaped. P orbitals have dumbbell shaped and a distinct orientation. Okay, P orbit. Electron. Hmm. Interesting. Look at that. They're doing this kind of... No, because they're not... That is not... Oh, wow. Oh, shit. That is amazing. Whoa. Okay. Whoa, look. Can you see that? Probability distribution of electron in 2p orbitals. Oh, hello. Can I click on that? Oh, I see that is the orientation happening there. Okay, that is really cool. Right. Electrons in a 2p orbital have lower ionization energy because they are, on average, a little further from the nucleus, and so a little more easily removed compared to 2s electrons. That said, the overall average atomic radius of boron is smaller than beryllium, because on average, all its electrons spend more time close to the nucleus. Oh, whoa, okay, that's interesting. Let me read that again. Electrons in 2p orbital have lower ionization energy. Okay, this makes sense because they are, on average, a little further from the nucleus. That makes sense. And so a little more easily removed compared to 2s electrons. Makes sense. That said, the overall average atomic radius of boron is smaller than beryllium because on average, all its electrons spend more time closer to the nucleus. Its average radius. Oh shit. So this R is a probability based. No, well, it's the average based on all the probability of movement. I did not know that. That is fascinating. I guess it makes kind of sense. So we got this again. And this R is, or the the size of R is determined through a function of probability. And this probability function P is equal to the the what did they say? It was the orientation. Orientation um, and energy. So some kind of distribution of these determines R. So R is equal to the probability, or R run through the function of probability, and that is based on rotation energy, or at least a probability of Ah, yeah. Oh man, really? Something like that. Interesting. Okay, that makes complete sense. The slight drop in ionization potential between nitrogen and oxygen has a different explanation. Oh God. The electron configuration of nitrogen is typically written as 1s2, 2s2, 2p3, but this is misleading. It might be better written as 1s2, 2s2, 2px1, py1, pz1. I see this is orientation because they are okay with each 2p electron located in a separate p orbital. These p orbitals have the same energy but are orientated at right angles to one another. This captures another general principle. Electrons do not pair up into an orbital until they have to 67. Well, at least it doesn't say 69. This captures another general principle. Electrons do not pair up into an orbital until they have to 6. Since the p orbitals are all of equal energy, each of them can hold one electron before pairing is necessary. When electrons occupy the same orbital, there is a slight repulsive and destabilizing interaction. When multiple orbitals of the same energy are available, the lowest energy state is the one with a single electron in an orbital. Nitrogen has all three 2p orbitals singly occupied. Nitrogen has all three 2p orbitals singly occupied, and therefore the next electron, which corresponds to oxygen, has to pair up in one of the p orbitals. Thus, it is slightly easier to remove a single electron from oxygen than it is to remove a single electron from nitrogen, as measured by the ionization energy. To pull together a set of seriously obscure ideas, the trends in ionization energies and atomic radii indicate that electrons are not uniformly distributed around an atom's nucleus, but rather have distinct distributions described by the rules of quantum mechanics. Ah, this is lovely. This is so lovely. I'm so glad I'm learning this. While the details of these rules are derived from rather complex calculations, we'll get into them, and involve the wave behavior of electrons, we can cope with them through the use of quantum numbers and electron probability distributions. Typically, oh, sorry. Typically, electrons in unfilled shells are more easily removed or reorganized than those in filled shells, because atoms with unfilled shells have higher effective nuclear charges. Once the quantum shell is filled, the set of orbitals acts like a shield and cancels out an equal amount of nuclear charge. The next electron goes into a new quantum shell and the cycle begins again. This has profound implications for how these atoms react with one another to form new materials, since, as we will see, chemical reactions involve those electrons that are energetically accessible, the valence electrons. We could spend the rest of this book, and probably one or two more, discussing how electrons are arranged in atoms, but in fact, your average chemist is not much concerned with atoms as entities in themselves. Unfortunately, I am. We should find another book. As we have said before, naked atoms are not at all common. What is common is combinations of atoms, linked together to form molecules. From a chemist's perspective, we need to understand how, when, and where atoms interact. The electrons within inner and filled quantum shells are relatively inert, which can be translated into English to mean that it takes quite a lot of energy from the outside world to move them around. These electrons are often referred to as core electrons. They generally play no part in chemical reactions, and we really do not need to think about them much more, except for the fact that they form a shield between the nucleus and the outer electrons. Okay, well, we'll just read on. The results of their shielding does, however, have effects on the strong interactions, commonly known as bonds, between atoms of different types, which we'll discuss in chapters 4 and 5. Reflecting back on chapter 1, we could think about the distinction between the van der Waals interactions acting between helium atoms and H2 molecules versus the bonds between the two H atoms in an H2 molecule. Bonds between atoms involve the valence electrons that are found in outer and usually partially filled orbitals. Because of the repeating nature of electron orbitals, it turns out that there are patterns in the nature of interactions atoms make, a fact that underlines the organization of elements in the periodic table. We will come back to the periodic table once we have considered how atomic electronic structure influences the chemical properties of the different elements. Question to ponder. What would a graph of the potential energy of a hydrogen atom look like as a function of distance of the electron from the proton? Oh, these sound good. Maybe we can do these. Maybe we can do these. Yeah, I could do a Python program. We can take a few electrons. What would a graph of the kinetic energy of a hydrogen atom look like as a function of distance of the electron from the proton? This is all really, really necessary stuff. What would a graph of the total energy of a hydrogen atom look like as a function of distance of the electron from the proton? Wow, this is great. This is absolutely great. Let's refresh this page to get that URL. This is great. Talks about energy in electron shells. Let me just see if I can go back to chapter 1. Yeah, look, all this stuff. Oh wow, okay. So this is an awesome book. Chemistry, chapter 1, text 1, chapters. Oh yeah, alright, let's do it. Index of clue chemistry chapters. All chapters here. Cool. Let me check my time. Yeah, 12 o'clock. I will leave it here. I know it hasn't been very long, but that was a good little session. I've actually learned something. So yeah, keep learning, keep loving. Bye for now.